determine the direction angles of the vector v is equal to I hat plus 2k hat plus 4j hat. So the first thing we want to understand in this problem is what are the fabled direction angles of a vector? Well, simply put, it's the angle between the vector itself and each of the positive coordinate axes in its space. Okay, so let's visualize this. That will make this much easier. Give myself a little coordinate space there. 3 dimensions. Nope, that was bad. We'll just do that. Sorry for the not perfectly straight line. Okay, we have x, y, z. Okay, so let's go ahead and think about this. We have 1i, 2k, and 4j. So we have, let's say, 1i, 2k, and 4j. This is not drawn to scale necessarily. And in fact, I don't even need, I'm generally pointing up here. Okay? And let me angle this a little bit, maybe like this, so as to not confuse it with the x-axis. And let me also make it red. Okay, so now let's drop this into the xy plane. Okay, there's x, there's y, and we have z. Okay, so here's our vector v. Here's our vector v. Now what we're asking about is the angles between v, the vector itself, and each of these positive coordinate axes. So here's the x-axis, right? Oopsies. Here's the x-axis. We want the angle between v and positive x. We call this theta x. Similarly, here's the y-axis. Okay, here's the unit vector y or unit vector k. We want the angle between v and k. This is theta y. And finally, we have the z-axis, and you probably see where this is going. We want the angle between v and z, and that is theta z. Okay, or v and k, where k is the unit direction. Oops. Look at this. I wrote the problem wrong. I, J. Okay. There we go. Hopefully that wasn't, if you noticed that and you said, something seems fishy. Well, it was fishy, and I just flipped those 2 letters. Oopsies. Okay, so this is somewhat hard to visualize, but let's think about a triangle, say between v and the x-axis. Okay, so if I have, let's move around in 3-dimensional space such that we're looking at that triangle, the triangle created by I hat, v, and some hypotenuse. Actually, v would be the hypotenuse. Some opposite angle. So here's, I'm just going to try and make this clear here. Here is the blue arrow here. Okay, blue arrow. Now, here is our original vector v, red arrow. Now, imagine some opposite angle here. That would be like right here. Oops, man. Like that. Okay, that black line corresponds to this black line. So we've moved around in space such that we're looking at this head on, right? And here's what we have. Now, the theta x, the direction angle of vector v with respect to the x-axis is theta x. That is this blue guy right here. And actually, let me make it blue so everything is nice and consistent. X. Similarly, if we were to draw an opposite angle between this green vector, j hat, and the vector v, and similarly k hat and vector v. So what we're asking about is the angles between the positive axis, coordinate axis, and the vector itself, notably not the vector projected onto some other plane, okay? Now let's think about this. Well, what is this angle here? How can we determine this? We happen to know 2 of these quantities, right? We can know this blue quantity, and we know this red quantity. What is this red quantity? It's simply it's simply, and let's talk about magnitudes here. So the directions, the directions give rise to this angle. Now we're talking about magnitudes. The length of this line is the magnitude of vector v. What is the length of the blue line? That would be, think about it, submit your answers. That would be the x component of v, right? Now we have an adjacent length here, and we have a hypotenuse length here. So everyone remember back to SOHCAHTOA, right? The mnemonic, SOHCAHTOA. Well, we have an adjacent and a hypotenuse. That looks a lot like a cosine to me. That is to say, the cosine of theta x, that's the name of this angle here, is equal to the adjacent over the hypotenuse. So what we have is that the cosine of the theta x is equal to, where the adjacent is vx over v. Look at that. Now, let's think about this. If we were to do this for all three, cosine of theta, and this, you can extrapolate this. This is a fun, maybe draw it out. Think about why this works in all three dimensions. Cosine of theta y is equal to vy over v, not u. And cosine of theta z is equal to vz over v. If we were to solve for these, what we want is the theta, right? We don't know theta, but we know everything else here. So really what we can kind of conclude here is that theta x is equal to the inverse cosine of the x component of v over the magnitude of v. Similarly, theta y is equal to the inverse cosine vy over v, and theta z is equal to the inverse cosine vz over v. Okay, and now all we have to do is plug things in. We could determine v, as usual, is equal to the magnitude of v. Here we go. The magnitude of v. This is equal to vx squared plus vy squared plus vz squared, because it just is. That's the definition, thinking about the Pythagorean theorem there. So we can determine that, and then we have vx up here. So, to actually follow through and plug in, we have 1, 2, and 4 are our components. So we have, let's solve this really quick, is equal to 1 squared plus 2 squared, which is 4, plus 4 squared, which is 16. This is equal to 5 plus 16 is 21, root 21, okay? So this is equal to the arc cosine or inverse cosine of 1 over 21, where this 1 is the x component of v, right? There's an implied 1 here, 1 times I hat, right? But we can leave that out. Okay, so that's our 1. Similarly, what would the other two be? Let me come back over here, is equal to, we know that the denominator is root 21, and we can even know that for over here as well, root 21, right? It's all the same term. It's the magnitude of v. That is the hypotenuse, that's this guy right here, of each of these triangles that we've made. Vy is 2, Vz is 4. Boom, boom. And then if you'd like to actually calculate these into degrees or radians, by all means, go for it. But this is what we have. These are the direction angles of the vector v. And with these, we can specify the direction of the vector v using these angles with respect to these axes.